Hello, this is Pat Kelly. Okay, in this problem, they give us a differential equation. The instructions ask us to use the integrating factor method, where we can get the integrating factor down to a function of just x or just y, and get the general solution to the differential equation. Okay, so a lot to take in, but that's actually what I've got set up for us in terms of the thought process. Is that whole mention in the directions about getting the integrating factor as a function of x alone or as a function of y alone comes down to these two different checks that you do. And the checking that we do is you work out the expression on the left and you ask yourself, does that end up being just a function of x? Or look at this equation and do similar work on the left and ask yourself, does that end up being a function of just y? Okay. Now when you're doing these problems on your own, you might even ask yourself, well, which of those two checks should I do? Which one should I start with? And you know what? You don't know typically. What you typically do is just jump right in there and do the first one. And if you get a nice expression that only depends on x, you're good to go. Go find your integrating factor and continue on in the problem. And of course, I'll show you that in this particular example. But if you don't get an expression that involves just x, you don't give up. You just move on to the other check, the other equation over there. Do the left-hand side, see if you can get something that just depends on y. Okay? So it might be a little bit of guess and check at first. Now I'm going to get started on ours, but I'm also going to explain that I feel very confident that the first equation is going to work, not the second. And the reason I feel confident about that, I'll give you some insight, is because of that denominator right there, that capital M. You know with these exact differential equations what m and n refer to. So the m here is the factor in front of dx, right? That's your m. And the n, while I'm at it, while I'm doing my labeling here, the n is what's being multiplied by the dy, so tan x for me. So the insight that I mentioned was that that second equation, that denominator of m, that's not going to work for me in this problem to end up being a function of just y, because m is x plus y, right? So your denominator would have both x and y in it. You're not going to get y alone. So I feel pretty confident that this first equation is going to work. Let's try it. Alrighty. Okay, so when I'm looking at this first equation, you got to know this notation. You know what m and n are, but the subscripts there are suggesting partial derivatives. So the partial derivative of m with respect to y. That's going to be the first term in my numerator up there. So I'm looking at the partial derivative of this with respect to y, and that's just 1. So that becomes 1 minus, the subtraction comes from here, and then the n expression, and I'm doing the partial derivative with respect to x. So the derivative of tan x with respect to x, that's your good old secant squared of x. Big divided by. Your denominator here is capital N, which is your tan x. So tan x. Okay, and does that equal h of x? Maybe as a question mark at first when you're doing these problems. Does that equal a function just involving x? Yes. Okay, so that worked for me. All right, now moving on. Now you use that to find your integrating factor, okay? Now your integrating factor, let me slide a little bit over here. I want to leave myself some space. My integrating factor is always e raised to the integral of h of x dx. Or if your second equation had worked, this would be a k of y dy, right? The space I left for myself here is we now need to find this integral of h of x dx, that exponent right there. So here's my h of x. I need to integrate that. And as I do that here, let me actually even do a rewrite. a simplification, because that numerator, if I use your good old Pythagorean identities from your trig, got to know your trig stuff, that's actually a minus tangent squared. So this is minus tangent squared of x in the numerator. Your denominator is still tan of x. So you can see that that simplifies to just minus tan of x. Okay? I like that better coming back over here to our integrating factor work, because now this actually equals e raised to the integral of just minus tan of x dx. And I'll just try to highlight this with another color, because just in your exponent, you have to know how to integrate tangent of x dx. It's been a while, hope you remember those, but that does end up equaling, if I replace everything that's squiggly there in yellow, that ends up equaling, I'll underline it as well in a minute, a negative natural log of cosine of x. I got to be careful. It's actually a minus. The integral of tangent of x is a minus, but there's another minus there. That does end up becoming positive. And here's the corresponding squiggle if it helps. That integral becomes natural log of cosine of x. Okay, so it looks involved, but I actually like this a lot, because we have e raised to a natural log power. Those kind of cancel each other out. You actually end up with just cosine of x. I say cancel each other out. I don't want you to think I'm doing any magic. That's a property of logs, okay? All right, so that cosine of x is my integrating factor. Now I'll slide back over here, and the idea with the integrating factor approach is you now go back to your original differential equation and multiply by that integrating factor. Okay, so I'm going to have the x plus y that was there to begin with times cosine of x times dx plus, and I'm also multiplying this tan x by cosine of x. Let me do a little bit in my head here though, because tangent is, you know, sine over cosine. Cosines are going to cross out. That just becomes sine of x dy. And you still have the 0 on the other side. You multiplied by cosine of x, but that's still just 0. Okay, that's good. That's good because now we have an exact differential equation. So I'll switch colors again here, just because when you go to get your general solution for an exact differential equation, that's where we're looking for that little f of xy, and it equals the integral of either m or n, and I'm looking here in this version of it after I've done my multiplying, not that m and n up there. Your choice. I'm going to grab the sine of x, it's smaller. Let's just integrate that sine of x. And since this is the n expression, the one that's paired with dy, I'm actually integrating that with respect to y, which actually makes it really easy to integrate, because that sine of x is a constant, so I just have y to the 1 power times sine of x, plus, you don't want to forget, there could have been more that involved x, so we express that as g of x, some function involving x. Okay, we need to find that g of x, though. I could switch colors here again. In order to find that, I hope you've been doing your homework. This routine should look familiar at this point. You take your f and do a partial derivative with respect to x. So I'm differentiating this guy with respect to x. Sine of x becomes cosine, and that y is a coefficient. So y cosine of x plus g of x, if I differentiate it, with respect to x. Best I can say is g prime of x. But what that allows me to do is take this partial derivative that we just found and make sure that it exactly matches your m expression. Okay, so I'll say this must equal, we're setting this up, we're saying it must equal, and I'm looking here, and I'm going to go ahead and distribute through the cosine of x. It'll be easier to work with. X cosine of x plus y cosine of x. And now I do my balancing act. My balancing act here, you can see y cosine of x, y cosine of x. So what I just figured out, I'm eyeing up some space here because I'm going to go over to the side here. What I just figured out is that this has to end up balancing with that. So g prime of x equals x cosine of x, which I can then use to find just g of x by doing an antiderivative. And I'll pause and take a breath here for your sake, because what you need to realize is now you're integrating this, which we did integrals chapters ago, but you can't forget your methods and know how to do these integrals. This is actually an integration by parts. You break that down and do an integration by parts, or maybe you're allowed to use one of your integral tables. Either way, what you should get is that this anti-differentiates to x sine of x plus cosine of x. Okay? All right, so a little bit of work went into that step, but it's old work for us. You should be able to do that. What that tells me now then is, I think I'm a little bit excited because I think I've got an answer now. That tells me that I now have my general solution. That's what they wanted from us. The general solution is your f of xy expression from here, y sine of x plus g of x, which we now know from our work over here. That's going to be plus x sine of x plus cosine of x. That's all your f of xy. That's the left side of an equation, and on the right-hand side, there's still some unknown constant. For a general solution, there's going to be that unknown. Okay? All right, a bit of work. Make sure you practice some more on your own, though. Okay?